We can generalize the statement of the pigeonhole principle, and instead of saying that we should have at least two objects in a box, we can give a more specific value for the minimum number of objects in a box. Again, assume that n and k are positive integers where n is greater than k, and we are trying to place n objects into k boxes. In this case, there is at least one box containing the ceiling of n over k objects. Now, briefly, let's remember what the ceiling function does. This is equal to, well, a is a real number here, so the ceiling of a real number is the minimum integer that is not less than a. So if a is an integer, then its ceiling is equal to itself, or for instance, ceiling of 3 is equal to 3, ceiling of 5 is equal to 5, ceiling of -7 is equal to -7. Okay, if it's not an integer, for instance, ceiling of 3.2, the minimum integer that is not less than a, well, 3 is less than a, 4 is not, so 4 should be the floor of 3.2. Similarly, 3.2, 3.8 ceiling should be again 4. It's a little bit different with negative numbers, for instance, negative 3.5. Negative 4 here would be less than negative 3.5, so the ceiling of this should be -3. Okay, so this is not the integer part function. This is not a rounding function. You see 3.2 does not go to 3, it goes up to 4. 3.8 also goes to 4, but it's the ceiling function. So the generalized pigeonhole principle states that if you have n greater than k objects, where k is the boxes, you distribute them into k boxes, you will have at least one box containing the ceiling of n over k objects. Again, let's see this on an example. Assume that you have a group of 100 people. Among these, we are looking at birth months. Okay, so birth months are going to be my holes or my boxes. Okay, there are 12 of them: January, February through December. And I'm going to distribute 100 objects, the people, into these boxes. So even if you even them out, okay, in at least one of the boxes, you will have 100 divided by 12, and take the ceiling, you get 9 people sharing a birth month. Here's another example. What is the least number of area codes to guarantee 25 million phones in a state can be assigned distinct 10-digit number of the form given here, where you have this area code 3 digits and the remainder 7 digits is the unique phone number. And here X represents any digit 0 through 9, and N represents, now you have one N here, another N here. These are not the same numbers. It's a little bit misleading notation, but N here represents any digit between 2 and 9. So what we mean by this notation is the leading number here should not be 0 and should not be 1, and the same goes for this leading number. Okay, so this format for the subscriber number, let's say, gives me 8 million distinct numbers in this form, because I have 8 choices for n, right? And then I have 10 choices for x, and when you use the product rule, you get 8 million distinct numbers. But I have in total 25 million subscribers, so I would like to distribute these into area codes. Okay, so those with the same 7-digit number will be distinguished by the area code. That is the idea. Some people will ultimately share their 7-digit phone numbers, but since we assign them, we are going to assign them different area codes. Hopefully, they are going to be distinguished by those. Okay, so we are looking for the minimum number of area codes. So divide 25 million by 8 million and take the ceiling. Well, this is of course 3 point something, but take the ceiling, you get 4 area codes. This is the minimum necessary. It doesn't guarantee you, but what it says is you cannot do this with 3 or less, because if you assign 3, the maximum you can get to 3 times 8 million, that's 24 million. You cannot hit 25 million with that. So what this is saying is you need at least 4, and who knows, maybe more.